The functions that we've come across so far can be viewed as one variable in terms of another. Usually y is a function of x. So another way of saying this is that y is usually by itself on the left, or f of x, and then on the right side of the equal sign are just expressions that have x in them. And sometimes you get functions like, or relations, equations like the one you're staring at now, which can be solved for y if we wanted to do that. But we're going to see that there are going to be many types of equations that for which it's not easy to solve for y in terms of x. And so there's a technique, a differentiation technique called implicit differentiation, which is really just an application of the chain rule that'll allow us to find what the derivative of these kind of crazy looking equations are without actually having to solve them for one variable. So this is let x squared plus y squared equal 25, and we're trying to find the slope of the circle at 3, 4. So here's my circle down here. It has a radius of 5. So I guess I'll mark that point as 5, 0. And 3, 4 is roughly around this area here. And so we're looking for the slope of this somewhat poorly drawn tangent line. So one thing we should notice is that it's probably going to be negative. And it's also the top half of this circle. So we're going to do this in two ways. We're going to first treat this like we've been treating any other type of equation, and we're going to solve this for y. So I'm going to call this the old method. This is like the old method of doing things. I'll label that 3, 4. So let's try solving this equation for y. So if I subtract x squared, I get y squared equals 25 minus x squared. And then if you square root, you get y equals, plus or minus the square root of 25 minus x squared. And y equals minus the square root of 25 minus x squared would give us the bottom half of this circle. And y equals the square root of 25 minus x squared, or the positive version of that. That will give us the top half. Now what we'd have to do is, if we want to continue with this problem in terms of finding the derivative, we're going to have to ignore the fact that we came up with two equations. We don't care about the bottom half in terms of what we're trying to find, so we focus on this, the top half, the equation that represents the top half. So let's focus on that. So dy dx, the derivative, is just going to be, I'm going to rewrite the square root of 25 minus x squared as 25 minus x squared to the 1/2, which will allow me to use the power rule. So it'll be 1/2 25 minus x squared, and then don't forget to multiply times the derivative of the inside, which is negative 2x, because of the chain rule. Alright, and so then a little cancellation. This 1/2 cancels with the negative 2, and we end up getting, oops, I forgot something. I forgot to diminish the power up here. That should be to the negative 1/2, right? I got to subtract 1 after I do that. So when I rewrite this, I can express it as x, or negative x rather, divided by the square root of 25 minus x squared. So there's dy dx. So that's an equation that gives us the derivative of the top half of the circle. Okay, it'll give us the tangent line to any point that's on the top half of the circle. So let's evaluate it at x equals 3, since we're trying to find it at the slope at 3, 4. So dy dx, I'm going to use this notation. I'm going to draw a vertical line at x equals 3 is going to be negative 3 over the square root of 25 minus 3 squared, which is negative 3 over the square root of 16, which is negative 3/4. So the slope of this is negative 3/4. Slope of that tangent line. Alright, so that wasn't so bad. It was a little annoying that we had to solve this equation for y. Let me show you the advantage now of using this new technique called implicit differentiation. And you're going to see that it'll prevent us from having to solve. It's going to prevent us from having to solve this equation in terms of y. So I'm going to say using implicit differentiation. And so an important assumption has to be made before we do this. We're going to assume that y is some function of x. In other words, in theory, we could solve for y and have all x's on the other side, but we're going to just assume that it can be done, and then we're just going to use the chain rule. Alright, so here's how it works. You take x squared plus y squared equals 25, your original equation. And then what you do is you take the derivative of both sides, as though taking the derivative is an operation you can do, which it is. So I'm going to take the derivative of both sides with respect to x. And so the derivative of the right-hand side is simply 0, because the derivative of any constant is 0. The derivative of the left-hand side, well, we can use the addition rule. The derivative of x squared is 2x. The derivative of y squared, and this is where you have to slow down a little bit, the derivative of y squared, well, remember that y is some function of x, right? So that y really isn't a y, it's stuff with x's in it. So it's stuff with x's in it squared. That means that the way we take the derivative is going to bring the 2 down, leave the inside alone, so that's 2y, but then we get a times by the derivative of the inside, which would be the derivative of y, which we're just going to express symbolically as dy dx. Okay, so that's the key step right there, and that's just the chain rule. So most students get confused by why we're doing that. It's just the chain rule. Now what we don't want to do is solve for this, right? We're interested in the derivative. We want to isolate this. So we'll minus 2x from both sides. And we'll get that 2y times dy dx is equal to negative 2x. And then we'll divide by 2y to get that dy dx is equal to negative x over y. Now, there's an advantage to what we just found. We just found another expression for the derivative, and it's in terms of the x and y coordinate of any point on this circle. Which means that if I want the slope at the point 3, 4, I'm just going to plug in. I'm just going to plug in 3 for x and 4 for y, and we get the exact same answer. So the advantage, again, of doing implicit differentiation is we don't have to solve for y. We just need to use the chain rule and then solve for that derivative. And it also sends us right to the point of interest because it often expresses the derivative in terms of both the x and y coordinates. Whereas on the left-hand side, the old method, we had to bring our prior knowledge of this circle in order to ignore the negative square root of 25 minus x squared to focus on the actual one we wanted to use. So this is just an introduction to implicit differentiation. I'll do another example in a following video, but what you should take away from this is just that we have another technique, nothing more than the chain rule, and it's going to help us. It's going to help us find derivatives of relations and kind of crazy looking graphs without actually solving for y in terms of x.